Now, my dear students, today we will discuss about the stereonet, how stereonet is being prepared, and how this stereonet is being used to solve the problems related to attitude of birds, problems related to plotting of linear features in stereonet. So, the planes are plotted in the stereonet as great circles. Linear features are plotted in the stereonet as points. In order to draw the great circles for representing the planes, the plane is imagined to pass through the center of a sphere. First, its spherical projection is made in the sphere. This plane is represented as a circle touching the periphery of the sphere. So, let us say this is the sphere. This is the sphere. This is the center of the sphere, and we have imagined a plane passing through the center of the sphere, and this is the circular trace on the periphery of the sphere representing the plane. This is the dipping plane, and this has been passing through the center of the sphere, and it is touching the sphere at its periphery in this circle. So this is the circle representing the plane passing through the center of the sphere, and we have this portion at the lower hemisphere and this portion at the upper hemisphere. And if you take this point at the center, this will be the northernmost point, or we can say it is zenith point. And to represent this plane, how we will use it? We have to represent this plane in the equatorial plane of the sphere. That will be the representation of the plane in the equatorial plane. So how? So this is the dipping plane that has been projected. This is the dipping plane in the sphere, and we have this is the equatorial plane of the sphere. Let us say dip of the plane is theta. So this is the horizontal plane. This is this equatorial plane, the horizontal plane, and this is the lowermost point of the dipping plane touching the sphere. So this angle will be the dip, that is phi. Now, for spherical projection, the projection of the plane can be obtained on the equatorial plane. So, from this spherical projection, we can get the equatorial projection for this plane. How? For this purpose, projection lines are drawn from each point on the periphery of the plane at the lower hemisphere to the zenith point, say north pole of the sphere. So, this is the north pole of the sphere, and all the points which are coming in the lower half, all these points, they are connected to the northernmost point. So all the points in the lower hemisphere are connected to the northernmost point like this. So the points where these lines pierce the equatorial plane will be taken into account, and they will describe a semicircular arc like this in the equatorial plane. So this semicircular arc results by the points from the periphery of the sphere linking the zenith point and piercing the equatorial plane. So the points where these lines pierce are joined, it gives a circular arc. It is the part of a big circle. This cyclographic trace is the representative of the plane. So this is the plane. This plane is represented as a arc like this in the equatorial plane. So this cyclographic trace is the representative of this plane having dip phi. Thus, in this manner, we can draw planes in form of semi-circular arcs or in form of cyclographic trace of big circles. So how to draw these big circles once the deep amount is being known? That we can solve in a mathematical way. Now let us imagine the vertical plane passing through the center of the sphere along the deep direction. So this is the plane, this is the vertical plane that is passing through the center of the sphere and is containing the deep direction. So this amount, if this is the horizontal line in the vertical plane, so this amount will be phi deep, because we have imagined the vertical circle along the deep direction. So this will be the deep amount phi. And so this is a part of the sphere, this circle, vertical circle. So this is radius, this is radius. So this triangle becomes isosceles, and we can find out this OA. This OA will be equal to R tan pi by 4 minus pi by 2. This is this OA distance, where the line starting from the plane at the lower half, pointing the deep direction, is being joined with the zenith point. So this distance is the distance that represents the distance of the cyclographic trace from the center of the sphere. So by solving this triangle and taking this angle as phi, that is deep, we got OA distance as R tan pi by 4 minus pi by 2. If we take into account the horizontal plane with this line as the horizontal line, and we have this is the OA distance representing the part of the circular arc. This will be the circular arc which will come out of the plane through its projection into the equatorial plane. We got the OA, and this is the circular arc. So where is its center? If we detect the distance of this circular arc, which is part of a big circle, if we detect the center of this circle, it will be somewhere here. From the center, then we can be able to draw this circular arc in the equatorial plane to represent the planar body. So how we solve this? How we get the center of this circular arc which has been projected out of the plane into the equatorial plane? So that we are going to solve. So we have detected this distance. We transfer this triangle into the horizontal plane. So this is the cyclographic trace in the horizontal plane or the equatorial plane, and this is the OA distance that we have already found out. And as per the projection of this triangle, OBC triangle, into the horizontal plane, we can get this triangle, and we know, we find out this angle, we find out this angle, then we draw this line in the circular arc, divide it, draw perpendiculars, divide into two equal parts, and draw the perpendicular, so that this triangle comes into picture, which is an isosceles triangle. So this angle will be equal to this angle. We know this angle, we know this angle. This has been found out here. OXA, then this line is equal to this line, so isosceles triangle. So this angle, total angle, is equal to this angle. Perpendicular bisector by the center of the great circle, cycloramic trace of the plane. This is the cycloramic trace of the plane. Now we solving this. The center of the great circle is found out at y. So how we can get the OY distance in terms of these angles? By construction, this angle is found to be equal to phi, which is the deep angle. So we have drawn the perpendiculars, bisector, then we got the YAX triangle, isosceles triangle. So we have solved these triangles to find out OXA angle, OXA angle here, this angle is equal to this angle we have found out, and this angle becomes equal to and finally we got phi as this angle. So this is 90 degree. So in this triangle we got OY, equal to r tan phi. So this is the simple process of solving the angular relation in triangles, and finally we got phi, and by taking phi into account, we got OY is equal to r tan phi. Thus, for different angles of dip, that is phi angle value, r tan phi can be found out, and hence circular arcs for different dip angles can be drawn from the center of the equator plane, that is O. All those great circles are shown as north-south oriented big circular arcs in the stereonet, which is used to represent the dip and striker planes. So this is the way how these circular arcs representing planes have been found out, because we know the OY is equal to r tan phi. So this is OY for different arcs, different circular arcs. So these circular arcs, the great circles, which represent the planes. Each circular arc represent the plane, and this point represent the highest dip. If you move along this arc to the periphery, the dip amount gradually decreases and finally becomes zero at this point. So this line will be the strike. This is the maximum dip, and dip amount decreases or it becomes apparent dip. These are the apparent dips. These points on the circular trace, they represent the apparent dips, and this is the maximum dip, this is true dip. So if we move along this arc, we get apparent dips. The arcs are drawn by taking into account this OY value. OY is equal to r tan phi. So we could know how these circles are, these great circles are being drawn in the stereonet. So this is the north-south line, center. So from the center we draw a horizontal line like this, east-west line, and on it we plot OY and we get the circles, part of the great circles like this. Similarly along this line we can get the circles like this. So these are the great circles which represent planes. And this amount is the maximum dip, because this amount, each line is representative of a particular dip, and the furthest this circle from the center, lower is the dip angle, and dip is 0 at the periphery. So dip is 90 degree at the center. So these circular arcs start from 0, 10, 20, 30 like this, and finally the straight line is the 90 degree dip. So these great circles in the stereonet represent the dip angles. So the dip angle, further is the arc from the center, lower the dip angle, further is the arc from the center. Vertical planes appear as straight lines through the center. So you could know how these great circles are being plotted and how they indicate the planes. So this will be the true dip. If you move along the arc to the periphery, to this north-south line, that will indicate gradual fall of dip in form of apparent dip. It will go on decreasing, finally it will become 0 at the strike line. So this will be the strike line. Now we will consider how planes that do not pass through the center of the plane are represented in the stereonet. In the previous discussion, we discussed about the plane which was passing through the center of the sphere. We are taking this at the dip amount, and we have represented this in the circular section at the equator in form of an arc. Now we will discuss about the planes which do not pass through the center of the sphere. If this is sphere, imagine a plane like this. So how it will be represented in the equatorial plane of the sphere? That we will discuss. These are represented as small circles. To draw such small circles, let us imagine a vertical section through the center of the sphere and a plane perpendicular to that of the vertical plane, but not passing through the center. MN be such a plane. So we have taken a vertical section through the center of the sphere. This is the vertical section or vertical plane, and we imagine a section perpendicular to this vertical plane, and let it be the MN section, this section. So this is the vertical circle, this will be the zenith point, and if this is the section, this section will be a circle in the sphere. So if you touch each point to this zenith point, then we will get the representation of this circular section on the equatorial plane, on this equatorial plane. So we have taken the vertical section, and we have taken the section MN perpendicular to that vertical section, and we have projected this circular section into this vertical plane. How? If we project this N point to the zenith, it will pass in the vertical plane at the point I. If we project the point M, it will appear at the point Z in the equatorial plane. So this will be I, and this M representing the equatorial plane will be here at this point. This will be J. So I is the projection of point N in the equatorial plane. J is the projection of point M in the equatorial plane. So Ij will be the circle, that will be projected by this Mn cross section into the equatorial plane. So this will be the circle that will result out of this Mn section perpendicular to the vertical section. So this is the circle that will come into picture out of this Mn vertical section perpendicular to this section, vertical section. So we have got I out of N, J out of M, and this is the circle. This is the circle in the equatorial plane whose center is C. Now let us say Mn trace an angle 2 alpha at the center. So this is radius, so this one will be alpha, this portion will be alpha, total will be 2 alpha. And according to the rule of circle, this angle will be alpha. This angle on the same arc, so this will be 2 alpha, in the periphery it will be alpha. So Mn section perpendicular vertical circle section sphere. This Mn section through sphere describes a circle with Mn as the diameter. How this plane will be represented in the equatorial plane of this sphere through projection. To project the Mn circle onto the equatorial plane, lines are drawn from each point on the circle to the zenith point, that is Z. Nz passes through the point I in the equatorial plane. Similarly, Mz projected to touch equatorial plane at J. Thus, Mn section of the sphere is represented as a circle on the equatorial plane, with Ij as the diameter, whose center is at C. Our aim is to find out OC, so that circular section placed at different angles with center O can be projected into the vertical section. Now let us say Mn circle make angle 2 alpha at O. As per the rule of circle, Mn will make alpha angle at the zenith. So now Ij will be equal to Oj minus Oi. Oj minus Oi. This is Ij. So in triangle, we can solve the triangles, and finally we get these angles, and by solving we get Ij equal to r tan pi by 4 plus alpha by 2 minus r tan pi by 4 minus alpha by 2. It becomes equal to 2r tan alpha. This Ij is equal to 2r tan alpha. Now we will find the central distance. So midpoint of Ij is the center of the circle, which is Ic. This will be half of this, so it will be r tan alpha. Now OC will be Ic plus Oi. Ic we know this, and Oi we know from the triangular relation. So we solving this, we got r by cos alpha as the distance OC from the center for making 2 alpha angle at the center. Thus, small circles not passing through the center but making 2 alpha angle at the center can be projected to the equatorial plane as small circular arcs in the following manner as shown in the diagram. So we got these centers, we got C points. So we got the distance OC, and we draw the circles for different angles. Thus we got these circles, this is O, OC, OC for different angles. For 10 degree angle, this is. For 20 degree angle, for this. 30 degree angle like this. For 40, 80, 90 like this. So finally 90 will be this line. Thus in stereonet, we have plotted the big circles which represent the planes passing through the center of the sphere, and we have plotted the small circles. These are the small circles which represent the planes that do not pass through the center of the sphere. So the stereonet is being prepared by taking into these great circles and small circles, and the great circles are represented in north-south form like this, and the small circles are represented perpendicular to the north-south line in form of this. It should be 0, 10, 20, 30, 40, 80, 90, 0, 10, 20, 30, 40 like this. So these are the small circles, these are the great circles. So each stereonet is made up of these great circles, So north-south oriented big circles are used to represent planes which have been imagined to pass through the center of the sphere, and these small circles perpendicular to north-south line representing the circular planes perpendicular to this line. They are represented as these small circles. So these small circles represent planes which do not pass through the center of the sphere. Different angles. For different angles, we have drawn these. Circles, small circles. In Wolf net, we have the B circles are perpendicular to small circles. Hence, in Wolf net, we have the angular relation between the great circle and small circle at right angles. So that's why they are called as equal angle net or Wolf net. But in Schmidt net, we have these small sections, these areas are all of same size, or we can say they have the same area. That's why it is called equal area net. Each unit has the same area, so this is equal area net in case of Schmidt, but in case of Wolf, it is equal angle net. This is equal area net. Now, we could know the stereonet, types of stereonet, and what are the great circles in the stereonet, and what are the small circles in the stereonet, and how the big circles are being drawn, how the small circles are being drawn, and how a big circle represents a plane which is deep amount, what is the true amount, true deep, what is the apparent deep, and all these things we could know. Now we will switch over to the deep and strike problems. We can solve these problems mathematically. We can solve these problems by drawing geometrical diagrams, or we can solve these problems by using the stereonet. So let us take a simple example. A bear dips 30 degrees along north, find its apparent dip along north 30 east. So here we have been given the dip amount, dip direction, and we have been asked to solve its apparent dip along a different direction. So let us say how mathematically we can solve. We know tan of apparent dip is equal to tan of true dip into cos of the angle between the true dip direction and the apparent dip direction. So here dip amount or theta is 30 degree given. Apparent dip is to be found out. This is to be found out, and this angle, the angle between the true dip direction and apparent dip direction has been given, because dip direction is along north and apparent direction in which it is determined is north 30 east. So this angle is 30 degree. So this angle is 30 degree. Angle delta is 30 degree. So putting the value, we got this. So alpha will be tan inverse of half. It will be, if you take 2 units at the base, tan theta. Tan theta is equal to P by B. If you take this is equal to half, so we can take 2 units at the base, 1 unit at the perpendicular to it, this angle will be alpha. Or we can solve it by taking into account the mathematical data sheet for inverse angles. We can see the data, and from that we can find out the angle. And the same problem, how we can solve it in geometrical method. So we have been given the dip direction along north, along which the dip is 30 degree, and let us say this is the north direction. This is north direction, and along that direction it is dipping at 30 degree. So perpendicular to that line, the dip direction, this should be strike, and we want to find out the apparent dip along north 30 direction. So for simplicity, let us draw the line like this. This is north. Let us show north 30 degree. Let us dip amount to this side. This is the strike. So this is the horizontal spacing. This is the vertical spacing. Let us say this is D for this amount 30. Now we will detect the apparent dip. How? We have to find out the apparent dip along north 30 east. So it touches the strike line at this point. We know the vertical spacing D. So perpendicular to this apparent dip direction, we draw a perpendicular like this at this point with the D spacing, and we join this. This will be apparent dip alpha. So that means spacing remaining same. This is D, this is for theta, and this is for alpha. So this is one triangle for apparent dip. This is the triangle for true dip. This is the angle for true dip, and this is the triangle for apparent dip. True dip triangle, apparent dip triangle. True dip, this is apparent dip. This is true dip, this is apparent dip. Now it is clear, I think. So we have to draw this strike line to know the vertical spacing. So let us say, imagine this is the dip amount. This is the dipping direction, dip amount. So if we see it vertically, so this angle will be 90 degree, and this angle will be the depth. This is horizontal line. This angle will be 90 degree. This will be depth. So this angle will be tan theta, dip angle. So these lines perpendicular to dip direction will be strike, and apparent dip in some other direction. Here you have to draw the perpendicular to this direction and get this spacing, depth spacing, in order to get the apparent dip angle. So this is the way how we have solved the problem in terms of drawing. Now, how we can use the stereo diagram to solve this problem? We have the stereonet like this. We have north, south. We have been told that the bed is dipping along north at an angle 30 degree along this direction. It is dipping 30 degree along north. So to find out this deep circle, what we do? Bring this north line to east-west line. Rotate this to this north east-west line. So what we do is, we take the net at the bottom and we place the tracing paper where we want to solve the problem over this net. So this tracing paper is called as overlay and the net is called as underlay. So by placing the overlay over the underlay, we draw the primitive circle first. Which is the outer circle of the net, and mark the north-south points and east-west points. So we have been told that the deep direction is along north at an angle 30 degree. So we now rotate this overlay so that this north point, indicated point, is brought to this position, this position of the net, east-west position. So now north is at this position. North marked point of the overlay is at the point E. So we have in the net, we have the circles like this, representing deep planes. So we have to read 30 circle. So draw this 30 circle over the overlay now. So over the overlay, the north point is here, and we have drawn this circle. This amount is 30 degree. So we have drawn the circle representing 30 degree deep. So this will be 30 degree point. We have been asked to find out apparent dip along north at east. Now rotate the arc to its original position so that north of this point matches with the north of the net. So we have got a circle like this in this condition. Then draw north at east, because this is 0, 10, 20, this will be, let us say this is 30, north 30 east. Draw this line. This will touch this great circle drawn at the point, say X. So this distance we have to calculate along the east-west line to see what is this angle, so that we can find out the apparent dip. Now again this line is brought to east-west line, and at this east-west line, this spacing is how much is read from the periphery, and it comes around 28 degree. So apparent depth will be 28 degree. So this is the way how we solve the problem in stereonet. So first thing is, we have to draw the primitive circle on the overlay, point out north, south, east, west. We have to, this is the overlay, we have to point out the north, south, east, west line, and then draw the strike line, draw the dipping plane, this is maximum dip, along this direction. From dip we will get here. These are the points for apparent dip. So along north 30 east, this will be the apparent dip. This is, if this is 30 degree, this cannot be 30 degree. As you go along this circle, from this point, from 2D point, if you go to this end, we will get gradual fall of dip from 30 to 0 at the strike line. So along north 30 east, here this line touches the point at X. So this distance is read from the periphery along the north south line, along the orientation along this direction. So we got the apparent dip to be 28 degree. Now let us take another example where the bed dips apparently along north 30 degree east, along north at 30 degree and along north 45 degree west as 45 degree. Find its true dip. So here we have been given two apparent dips. We will find out true dip. We have the mathematical relation that we can directly put to get the angle delta, so that we can get the strike line, and then we can solve the problem as we have solved in the previous problem. So how mathematically we will solve? We will take into account this formula. This is the delta, this is the strike line. We have been given apparent dip along north 30 degree, apparent dip along north 45 degree west 45 degree. So this is delta, this is alpha 2, this is alpha 1 according to our formula. So sigma is 45 degree. The angle between two apparent direction is 45 degree. Alpha is one apparent dip, alpha 2 is other apparent dip. So by putting all the values, we solve. We got delta as 20 degree. So we got this amount, this angle. This angle is the angle between one apparent direction and the strike delta. So first strike is along north, so it will be north 20. North 20 east. So the delta has been, so strike in north 20 east, south 20 west. And once we know the dip strike direction, we can find out the dip direction. We know the dip direction. So we know the angle between the dip direction and one strike direction. We know one apparent dip angle. We can get the true dip angle by following the previous formula. We can solve the value of this inverse by inverse table or data given in inverse table, or we can mathematically we can take use of drawing. Here it is root 6 minus 1, that means 2.45 minus 1, it will be 1.45. Cot inverse 1.45 is around, so this is 1.45, this is 1, around this. In this way you can solve. Cot 1.45, this is cot B by P. So it will have P1. We have to consider P1, B 1.45, and we have got this angle, which will be delta. And once we find out delta will be from the angle between the one apparent dip direction that is along north and 20 degree. So north 20 degree east, strike direction. Then we can solve the problem by using previous angle, the relation between true dip apparent dip and their direction. And we can solve this problem also by geometrical method. So this is the geometrical method. So along north we have the alpha 2, along north 45 degree west we have this is north 45 degree west, and this is alpha 1, this angle, this is alpha 2, this is alpha 1. So draw alpha 1 or the alpha 2. At any point you just draw a perpendicular to the apparent dip direction. Let us say this is the, so you measure this spacing, which will be depth. This is alpha 2 d, then alpha 1 same d. This is along north 45 degree west, this is along north. So north line perpendicular, d spacing, alpha angle. North 45 degree west, the same spacing is drawn, so that it will have the angle alpha 2, alpha 1. Same spacing d, such that this angle becomes alpha 1. So this angle of this length will be more, so that angle will be low. Or this angle, the length will be small, so that this angle will be more, the spacing remaining same. So for this purpose we have find out d here, and again plotted dip. At any place you draw perpendicular, measure d, draw a parallel like this, so that it will touch the angle dip, apparent dip angle at the point this, at the point, so this is the point, so this is the d we have found out. So this is the triangle for one apparent dip, this is the triangle for another apparent dip, this is d and this is d. So base of this d is here, So these base points are joined by another line, which will be the strike. These root points having d depth for the two apparent dips are joined, which will be the strike of the constant bed. Then draw perpendicular to that strike line from the center. This will be the dip direction. This will be two dip direction. Then, so this is the point of intersection between the strike line and the dip direction, two dip direction. Draw the spacing d in any direction, whether this direction or this direction, and join it. This angle will give you the theta, is the true dip. Or any, on this side you can also draw d spacing, then join, this angle will be theta. So in this manner we can find out the two dip. Let me discuss it again so that it will be clear. First we draw the, so along north it is, the angle is 30 degree. At any point you draw just perpendicular, so to know the spacing d. Then along north 45 degree line, this is the apparent dip direction, north 45 degree west. Along this we have the dip amount is 45 degree drawn. So to this line we have to find out the D spacing where it will touch this line. This is the baseline. This is the baseline of the dipping bed. So this is the direction of dip, and where we will get this D, so that it will touch this angle, this line, baseline. So draw perpendicular at anywhere D. Draw a line parallel to this. We will get this point. So this spacing will be D. So this is the root of D. This is the root of D. These two points are joined to find out the strike. And we know to strike the dip direction is always perpendicular. Draw perpendicular to this line. So this will be the dip direction for true dip. Then over this, along the strike, measure D, join this angle will be the theta, that is true dip. Now I think it is clear. Then by stereonet, how we can solve this problem? So along north, we have to find out the apparent dip. This will be apparent dip point along 30 degree small circles, this point. Similarly along north 45 degree west, the 45 degree will be here. So we got 2 points, one representing 30 degree dip, the other representing 45 degree dip. Then we try to bring this D1 point and D2 point in one great circle, D1, D2, in one great circle. So these are the two apparent dips. So this great circle, once it is drawn, it will show this mid portion will show the true dip, this portion. So these 2 points are brought in one great circle, D1, D2. This circle is the representative of the plane. So this midpoint will represent the apparent dip, which can be read from the periphery along the east-west line, of the net. So this is the way how we solve the problem for true dip and apparent dips. This is all about what I wanted to discuss about attitude of bed, true dip, apparent dip, stereonet, how stereonets are being plotted, how dip of planes are being plotted in the stereo net. In next classes, I will discuss about some other problems of dip and strike through use of net and through use of geometrical diagrams. Thank you.